All right, so it'd be remiss for me to introduce fluids and hydrostatics without mentioning Pascal's principle. All right, so what this principle says is that if we have an incompressible fluid, so let's say an example that would be a liquid, if the pressure at one point is changed, then the pressure at every other point in the fluid changes by the same amount, right? So implications of that and kind of what I mean by that, in other words. So looking at this diagram, all right, so we have some incompressible fluid and then two pistons on top of this container, where this container has the, a shape where the fluids are connected. So what pistons are, kind of simply put, it's some sort of mechanism. So I like to think of them, typically they're going to be, these circles of some sort of, let me find a picture for you guys. So something like here on the right. This is not the best image because this is simulating some sort of gas here, so something that's compressible. But I like to think of it as kind of like a piece of metal that usually fits whatever shape it's covering. So our fluid is completely covered, and that thing is able to move, whether it be up or down. A lot of times in fluid problems, so this unit, it's going to be some sort of weight on top of our fluid. Right, so that's what is meant here by a piston. But anyway, so in the situation we're dealing with here, right, so it looks like what this diagram is trying to show is that the situation here on the left, where we have a force that's acting downward on this fluid. Well, since there's a force acting downward and it's acting on some amount of area, which here the area on the left is depicted as smaller than the area on the right, then since the force is acting downwards, that means the pressure is going to increase on the fluid below. All right, so since that pressure is increased, assuming we're dealing with hydrostatic equilibrium, then the pressure along any horizontal has to be the same. All right, so this means then that the fluid on the right has a larger pressure on the bottom. Well, on the bottom I mean technically on the bottom as well, but I meant to say kind of the horizontal line with the connection of the tube. So if at, let's say, this point here, the pressure has increased, well, we have to compensate for that physically, right? There has to be, the hydrostatic pressure formula still has to compute. So to have that increase in pressure, well, that means that the depth of our fluid from the surface has to increase. So this height here has to increase, meaning that this piston then would move upward. Well, but I'll put a little asterisk on that. This would be definitely the case if our areas were the same. We'd have to be careful with that P0 term, the atmospheric pressure term. We have to do a little bit of computation here to be sure. But I'm going to move on from this. All right, so question for you guys. Let's suppose we have water being slowly poured into this container, and the water level has risen into the tubes in A, B, and C. All right. Water does not overflow from the tubes, and let's assume that the water has stopped pouring and everything has settled. So how do the water depths of the three columns compare to each other? All right, so since these tubes are all open to the atmosphere, once the fluid has stopped accelerating and we are in hydrostatic equilibrium, then all these three containers will have the same depth of water. So even though they have different shapes and have different volumes, the pressures will all be the same. So therefore the heights will have to all be the same. All right, so a couple problem solving tips before we wrap things up and kind of do a fun example. So of course, first things first, draw a diagram, right? So typically in these types of hydrostatic problems, we're going to be kind of sketching out whatever the container is, if there's any pistons, any useful boundaries. So what our kind of surface is, if there's a boundary between fluids, anything else that's going to help us out, so height, values, things like that. Second step would be determining what the pressure at the surface is. So it's easy to do if it's open up to the atmosphere, and this atmospheric pressure. Sometimes maybe our situation is, rather than the container being open up to the atmosphere, maybe we have some sort of container of fluid that has some sort of heavy gas on top of it instead of just air. So then we'd have a different pressure there. So it'd be the pressure of that gas. So that would probably be given to you in the problem, or there may be some method for you to compute that value. And the other situation, which we haven't talked about, but it's actually pretty interesting and pretty simple to compute, would be if we had a closed surface but had enough information to compute force over area. So an example of this would be like the pistons we were talking about just a moment ago. Right? If we knew the weight of the piston, well then, so that would be the force, and if we knew the area in which the piston was acting, we can then compute the pressure that's exerting on the surface of the fluid. Right? So that's actually a pretty fun thing to include in problems. So keep an eye out for that. Third, use horizontal lines to help you problem solve, since we know that the pressure will be the same as long as we're in hydrostatic equilibrium. And sometimes just be careful, problem might ask for gauge pressure instead of just pressure or absolute pressure. So just be cautious there. It's easy to basically solve your problem out and solve for just absolute pressure and then forget to then do that last step of converting to gauge pressure. And then finally apply formulas and solve. Oh, and of course I forgot one of the most important steps being check to see if your answer seems reasonable.